Okay, so this is part 3 of lecture 2, the last part for the lecture, and also the the great theorem of chapter 1. It is Hippocrates' quadrature of the loon. So this also will be the longest part of the lecture. Well, not that long, but certainly longer than the other 2 parts. So first, I'm going to write what we mean by a loon, what is a loon, and I'm going to state the preliminary results that Hippocrates used for this proof. So, a loon is a planar figure, is a plane figure that is bounded by 2 circular arcs, Okay, so it's like a crescent. All right, so what are the preliminary results that Hippocrates used? One of them, so preliminary, results that will be used. The first one is the Pythagorean theorem. The next result he used, or will be using in this proof, is an angle inscribed in a semicircle is a right angle. So let me write it. An angle inscribed in a semicircle is right. It's a right angle. And the third result, so this will take without proof, the areas of 2 circles or semicircles are to each other as the squares on their diameter. So I'll state this and I'll draw a picture just to show you what I mean. So the areas of 2 circles or semicircles are to each other as the squares on their diameter, as the squares on their diameter. Okay, so here's a little picture. Let's say you have this 2 semicircles. This is with diameter d, and this is with diameter big D. And this has area 1, and this is area 2. So what this statement is saying is that A1 over A2 is the same as the ratio of their respective diameters squared. Little d squared, capital D squared. So these are the preliminaries that will be used in the proof. Alright, so first we'll start with our construction and then we'll proceed with the proof. So first I'm going to write the proof here and draw the picture here. So first We'll start with a semicircle centered at some point O. First start with a semicircle centered at some point O. So let me just do that. Okay. Here's my semicircle, and this is the center. Let me name this A and B. This is the diameter. So that means that AO is equal to OB. Okay? And then we are going to construct the line OC perpendicular to line AB. Okay? And then construct OC perpendicular to line AB. This is it. That's the AC perpendicular to AB at point O. Then we'll draw lines. So draw lines AC and BC. Lines AC and BC. That means I'm connecting this two. Okay. The next thing we do is we are going to bisect the line AC in the middle. This is possible by previous remarks. You can do that with a compass. So let's say that we did this. So next, bisect line AC at point D. At point D. So let's say that this is the center. This is point D. And with center at D and with center at D and radius AD and radius AD, we are going to draw a semicircle. Draw another semicircle. Draw a semicircle. I'm gonna name that semicircle AEC. This arc here in notation means that I'm dealing with a semicircle. So, okay. So this is the middle with center at D and radius AD. I'm going to draw a semicircle. is good enough. It should have come all the way to here, but that's okay. That is because D is not perfectly in the center. Alright, so I'm going to draw the semicircle A. Let me name this point E, C. That's the semicircle AEC. So we have constructed the loon. Well, just name this point F. We have constructed the loon A, E, C, F. And we want to prove, and we want to show that A, E, C, F is quadruple. Let me mark it with red. At first, to show you what are we aiming to do. So this is the loon that we are interested in, and we want to show that this particular loon is actually quadruple. Okay. So, proof. The aim here is as follows. We want to show that area AECF, AECF, meaning the area of the loon, is exactly the same as the area of the triangle AOC. Are we going to be done? Should we be able to show this? Yes, because in the previous pages we showed that any triangle is quadruple. So if this triangle is quadruple, then so must be the loon if we show that their areas are equal. So that's what we're going to try to do. So we want to show that area AECF is the same as area of the triangle AOC. AOC. So we want to show that these two shapes have the same area. Okay. So by preliminary 2, what can we say about the angle ACB? We can say that it is right because it is an angle that is inscribed in this semicircle. So by preliminary 2, we know that angle ACB is right. Okay? And we also know that AO is equal to OC is equal to OB, as this is a semicircle with center at A, so all these three are radii. So we know that AO is equal to OB is equal to OC is equal to radius of the first semicircle, and that is so by construction. Okay. Further, we know, again by construction, we know also by construction that triangle AOC, that triangle AOC, AOC, and triangle OBC are right triangles, and triangle COB are right triangles. Okay, so we are going to consider these two. Consider these two triangles. Consider triangle AOC and triangle COB. What can be said? Well, AO we know to be equal to OB. AO is equal to OB. We know that by construction. Angle AOC is equal to angle COB. Angle AOC is equal to angle COB. They both are right triangles. I mean right angles. Okay? And we also know that the line OC is common to both. So the line OC is common to both. This means that by SAS, side angle side congruent scheme, these two triangles are congruent to one another. So by side angle side congruent scheme, then triangle AOC is congruent to triangle COB. That means they coincide, they have the same areas, equal angles are looking at equal sides, and so on. So since these two triangles are congruent, triangle AOC is congruent to triangle COB, then equal angles are looking at equal sides. That means that AC must be equal to CB or BC. Then AC is equal to BC. Okay, so where does that take us? Well, let's see. Also, since triangle ACB is right, ACB is right, then by Pythagorean theorem, then by 1, that is Pythagorean theorem, we have AB squared, the hypotenuse, AB squared is equal to AC squared plus BC squared. Okay? Or AB squared is equal to, since AC is equal to BC, you can say that AB squared, it is equal to 2 times AC squared, because the two are equal to one another from the previous step. Moreover, by preliminary 3, this result here, now we are going to consider 2 semicircles, or yeah, well, not 2 semicircles, but we are going to consider the following well, yeah, 2 semicircles. This semicircle AEC, that's a semicircle and the large semicircle. So, area of semicircle AEC, not the lune. I'm talking about this semicircle. A lune is not the same as a semicircle. Area of this over the area of the large semicircle, ACB, okay, is the ratio of these areas is the same as the ratio of their respective diameters. So what is the diameter for the first semicircle, or the smaller semicircle? That would be AC squared. AC squared, and this is AB squared. Okay. Well, AB, I just said from before that AB is twice AC. Well, AB squared is equal to twice AC squared, so we further write AC squared over 2 times AC squared, and that is equal to half. With other words, this means that area of semicircle AEC is half the area of the big semicircle ACB. With other words, AEC semicircle is half the area, of the big semicircle ACB. Okay, we're almost done. But we'll continue here. But area of the semicircle ACB, area of the semicircle ACB, it is equal to the sum of these two sectors, these two quarter of a pi, this one and this one. So area of the semicircle ACB, it is twice this area, AFCO. It is twice, that's a sector actually, twice the area AFCO. So this would mean that semicircle area of the semicircle AEC, so this implies that area of the semicircle AEC is the same as the area AFCO. Okay. So this semicircle and this sector have the blue part in common. So just going to play a subtracting game right here. Now, area of the semicircle AEC minus area of the semicircle AEC minus the blue part, minus area of the blue part, so that would be area AFCD, is the same as the area of the sector of this quarter of a circle here minus the blue one. So AFCO that square of a circle, minus minus the blue one. Okay, so they are the same area. So it is the same as area of AFCO minus the blue area, which is AFCD. So if these two quantities are equal to one another, from equal quantities, if you subtract equal quantities, the leftovers are also equal to one another. So this implies that area of the loon AEFC or CF, doesn't matter, is the same as the area of what's left here, which is the area of the triangle. Area of triangle ACO, which is what we wanted to show in the very beginning. Since triangle ACO is quadruple, then so would be any area that is equal to it. In this case, the area of this particular loon. Now, Hippocrates showed that this particular loon, constructed this way as we did, is actually quadruple. That does not mean that you can actually square or any other loon, arbitrary loon, is actually quadruple. In fact, if this was possible, then you can actually square the circle, or you can prove that the circle is quadruple. Mathematicians have tried to for centuries have tried to prove that the circle actually is quadruple, and it wasn't until the 1800s that it was proved that circle cannot be squarable, meaning it's impossible to construct a square with the same area as the circle. Now, here the problem lies with the number pi being involved in the area of a circle, and as it turns out, pi is not a constructible number or a so-called algebraic number, but is rather a transcendental number. It's actually an interesting read, is towards the very end of chapter 1, you can read that on your own, about transcendental numbers and algebraic numbers. Besides this particular loon, Hippocrates went on to prove that two other loons, again particular loons, were actually quadruple. There is one that is built upon a trapezoid, and then there is another one, and that's about it. He couldn't prove that other arbitrary loons were quadruple. Euler, it wasn't until 1700s that Euler did find or prove that two more loons are quadruple, and it wasn't then again until maybe 1900s that two Russian mathematicians proved that there are only those 5 loons that were previously discovered to be quadruple and no more. The 3 that Hippocrates proved and the 2 that Euler proved. So there are only 5 quadruple loons and no more than that. So that will conclude the end of lecture 2 and end of chapter 1. Until next time, when I post, or I'll start with the 3rd lecture. I will post together with this video, I will post some problems for you to work on that have to do with these ideas that we just talked about. So long everyone, and I'll speak to you soon.